Okay, so we've got this problem here, and this goes back kind of to the beginning of the term. We'd like to find the impedance E sub L for maximum power transfer. So we'd like to figure out what that impedance needs to be to get maximum power transfer, and then the value of that power. We notice right off that we cannot use the shortcut, right? Because we have this diamond here, we can't use the shortcut, so we're going to have to use the long method. The long method is, so no shortcut. So we have to do the long method, which means we have to find V open circuit, and then I have to find I short circuit, and then I can find that the ratio of those to give me Z Thevenin, right? Okay, so that's going to be our task. So we can cut through this thing right here and come up with, if we were to remove that load, come up with V open circuit, come up with I short circuit, and so forth. I think I've got this value Ix here. I think I'll put some assumed values in here. I could say that this is, when I say that's I1, we'll take our reference ground here. This is then V1, and we can say that this is V2. Do I need anything else? Probably a current here. Why don't I say that this is I2? Okay, so if I look at finding V open circuit, I would look at the equation. It's really a supernode equation, isn't it? I'm going to look at a supernode around here where I have I1 leaving, Ix leaving, I2 leaving. So I1 plus Ix plus I2. That's all leaving the supernode. Anything else leaving the supernode? I1, Ix, I2. How about here? Is there any current going in here? Not if that's open, right? Not for V open circuit. So I would just take that. I could say that that's equal to 0. So then I1, if I want to talk about I1, that would be the current going down through there. So I need to find this voltage across there. So I could say that that's really V1 minus 12, or 12 at 0. I can just say 12 divided by 1, right? Plus Ix, which is V1 divided by 2, plus I2. What's I2? V2 divided by minus J. Okay. Set that equal to 0. So there's one equation. Has two unknowns. Where's the other? So I could say that this is equation 1. You got two unknowns, so you got to find another equation. Well, there's always another equation when we use a supernode, isn't it? We could say that the second equation for this thing is that V2 is going to be equal to what? I could say that's V1 plus 2 Ix. Is that right? Which would be V1 plus 2 times what's Ix? V1 over 2. Okay. So we can say that V2 is equal to V1 plus another V1. Is that right? Those cancel out, so I'd have another V1. So V2 is equal to 2 V1. So I'd probably take that and substitute that back into that equation there. And we could then solve that. You'd probably want to solve that for V1 and substitute it in. And you could, at the end, get that V2. Unless, do you want me to go through the solution of those equations, or you solve those equations? Everyone's okay with that? Okay, so solve equations 1 and 2, and you'll get V2 which turns out to be equal to 9.6 at an angle of minus 53.1. And that's volts. And why am I interested in that? Yeah, because V2, there's no voltage drop across this inductor because there's no current going through it, so this has to be equal to V open circuit, doesn't it? Okay, that's V open circuit. Now, if we could have used the shortcut, we probably would have found that, and then we would have shorted the voltage sources, opened the current sources, and looked back into the element and seen what the equivalent impedance was. But since we can't use the shortcut because we have that diamond there, I'll just go through this again to calculate I short circuit. And going through that process, I'd put this current here. I could say that this is I short circuit, right? Okay, because we would end up just shorting that thing out. So when we go through it, we would have, again, I1 plus IX plus I2 plus now I short circuit, right, is equal to 0. So we have a very similar substitution, at least for a while. V1 minus 12 over 1 plus V1 over 2 plus V2 over minus J. Then I have to talk about I short circuit, don't I? What's I short circuit going to be? If this is shorted out, I have then V2 divided by what? J2? Okay, is equal to 0. So there's our first equation. We have two unknowns, V1 and V2, so we can use for the second equation, it's going to be exactly the same as this, isn't it? So my second equation here would be that V2 is equal to 2 times V1. Exactly the same thing again. Now I have two equations and two unknowns, so I can solve for V2 again. So solve 1 and 2. So solving 1 and 2, I come up with V2 is equal to 13.3 at an angle of minus 33.69, and that's volts. And why do I want that? Well, remember up here that I short circuit is that thing, isn't it? So I can say, therefore, I short circuit is equal to V2 divided by J2, which gives me 13.3 at minus 33.69 divided by J2, which we come up with 6.67 at an angle of minus 123.69. Too many significant figures, but that's okay for intermediate step. So that's the short circuit. So far, so good. Now, if we could have used the shortcut, we would have just had to do one or the other of those. We couldn't use the shortcut, so we had to do both of them. Well, let's put those together then. So we can say that Z Thevenin would be equal to V open circuit divided by I short circuit. So we've got the open circuit 9.6 at minus 53.1, and we have then the short circuit at 6.67 at minus 123.69. So this turns out to be equal to 0.48 plus J 1.36 ohms. Okay. So what do we know about for maximum power? That was where we first started seeing that conjugate thing, right? For maximum power, our Z load should be equal to what? Z Thevenin conjugate. So 0.48 minus J 1.36. So I can put this thing together into a circuit. I'll do the Thevenin model. You could do a Norton model if you wanted to. If you wanted to put the two impedances in parallel and use a current source, you could use the Norton model. I'm going to use a voltage source. So I'm going to take the open circuit voltage, 9.6 at minus 53.1. I've got the Thevenin impedance here. That's that 0.48 plus J 1.36. And then I'm going to put the load impedance. And for maximum power transfer, I know those have to be the complex conjugate. So 0.48 minus J 1.36. Right? So you could come up with all kinds of equations for the power. I could just go through the process here. If I talk about this current here, I, what's I going to be equal to? Well, voltage divided by impedance, isn't it? Total impedance. So I could say that that was 9.6 at an angle of minus 53.1. And if I look at the total impedance, adding these together, what do I get? 0.48 plus 0.48, right? The J's cancel. It's completely real then. So then I have 10 at an angle of minus 53.1. Okay, so I could say then that the power dissipated here is what? I guess we need to talk a little bit about power. It's been a while since we've done this. Average power is, we could say 1/2 I RMS squared times the resistance, right? Or it's what? No, that's not right. I don't want that 1/2 there. 1/2's not in that one, is it? Yeah, because it's RMS. I could, however, say that I have 1/2 I magnitude, if I'm using a magnitude, a maximum value, squared times R, right? Which is this? Yeah, it's not RMS, is it? So I want to use this one and say that I have 1/2 times the magnitude there, which is 10 squared, times the resistance. That resistance there is 0.48. So when you go through that, you get 24 watts. Okay.
The voltage that that was for power transfer voltage, 1/2 voltage squared by R.
Yeah, we do have one with the voltage, but remember this voltage that's given here is across both of them, and I really just want the power across that one. So I'd have to divide that voltage by 2. That's why, I mean, it's very valid to use the voltage. I mean, you could have 1/2 V maximum squared divided by R. That's certainly valid, but you have to be really careful of what voltage you're using. You would not want to use the 9.6. Good question. Other questions? Been a while since we've done something like this. Kind of nice. Going back to that. Questions with that? That will be easy money next week. Easy money. Okay. Easy money. Well, let's try another problem. It's a verbiage problem, so chances are it's probably power, maybe 3-phase, but most likely power. We're told that a plant currently at 64 kilowatts and 0.68 power factor lagging wants to improve to 0.92 power factor lagging, because a 0.68 lagging power factor is really bad. They are way too inductive. The power company is going to get after them. And so they want to improve to about 0.92 lagging. They're still lagging. So let's try and go from the verbiage to a picture on this thing. See what's going on. So we've got some sort of a load here. While in a true physical sense, this would be happening in three-phase. When we learned about these problems, we didn't necessarily do them in three-phase. If you wanted to do this in three-phase, you just do it for each of the three phases. But we're going to look at this as a single-phase problem. Okay, so we've got, currently we have 64 kilowatts, and we're trying to go from 0.68 lagging to 0.92 lagging. That's our power factor. And we're going to do that by putting a capacitor across here. Like that. We'd like to find out what the value of the capacitance is. So we're told the voltage here is 220 at 0. That's VRMS. We'd like to figure out the value of the capacitance we have to do this. Now, probably if we were careful, we could work out what the impedance is in here. But as far as trying to figure out what I have for resistor and what I have for inductor, no one's told me anything, have they? So the best bet on this problem is probably doing it with what? Power triangles, right? Okay, doing it with power triangles. So if I look at the, maybe I'll put the old system here. Old system. I can say that theta is equal to the arc cosine, the inverse cosine of 0.68. .68, which gives me 47.2 degrees. Okay, so if I look at this 64 kilowatts, that's average power, isn't it? So that would be the horizontal portion on this. So I have 64 kilowatts. And I have 47.2 degrees there. Okay. So what's Q going to be on this thing? 64K times the tangent of 47.2 degrees. You can keep that all in your calculator. You'll come up with 69 kVars, right? So then if I talk about the nu over here, we're going to take that theta is equal to the arc cosine, the inverse cosine of 0.92. Should give me a much smaller angle, shouldn't it? 23.1 degrees. So I now have this triangle that looks something like this. (23.1 degrees). This is still 64 kilowatts. And here now Q is equal to 64K times the tangent of 23.1 degrees, which gets me 27.3 kVars. Okay. So how do I get from this triangle here to this triangle over here? I'm going to have to add, to get from the old to the new, I'm going to have to add a triangle that looks like this, real small there, virtually nothing there, and this Q is going to have to be equal to a what? A negative. The difference between that, right? 69 less 27.3, which is what, about 42? Yeah, we'll just call it 42. Is that right? Yeah. Okay. So if I add this to that, I should get that. So that's the number I'm looking for. Okay. And we know the voltage across here, that's 220 at 0, right? That's why we put them in parallel. So you could say then that 42,000, 42K, is equal to V squared divided by, and we're just going back to our power, our reactive power would be V squared over the impedance. What's the impedance of a capacitor? 1 over omega C, right? So when I work this out, I've got 220, that's RMS, so I don't have to mess around with any halves or anything like that. I got 220 squared divided by 1 over, what's omega? 60 cycles. So omega would be 377 times your capacitance C. So you have one equation, one unknown, C. You can solve for that. C turns out to be equal to 2.3 milli. 10 to the minus 3. Takes a pretty good sized capacitor, millifarads. Question?
42 came from, we'd have to add that much.
Yeah, if I take the, how do I get from 69 kVARs to 27 kVARs? I have to add minus 42 kVARs via the capacitor. Other questions? You could play around with this and go back through these numbers and actually come up with what impedance you had and solve it like one of the labs that you did. I think one of the last test questions was a little different like that. Now that's probably good practice, but if you're given the powers, it's a lot easier just to do it with the power triangles. Questions of that? That's page 3. So we've got a three-phase power system here, a good-sized power system. We're told that we've got some line impedances here. This would, of course, be A and B and C. And the line impedances are 0.4 plus J.8. That's typical in all three lines. And we have two loads. It looks like load 2 is a Y-configured load. It looks like load 1 is a delta. And with load 2, we've got 2 megawatts at 0.8 power factor lagging, and that's total for all three phases. Okay, that's total for all three phases. And then load 1 is 1.5 megavolt amps, 0.75 power factor lagging, and again, that's total for all three phases. And we're told the loads require 4.16 kilovolts line voltage. So that's going to be the voltage across there. Has to be have a magnitude of 4.16 kilovolts. Okay, prior to the drop, or after the drop if you're thinking of coming from the source. So we've been given this with a lot of information in power. Maybe we'll explore that a little bit. So looking at load number 1. I haven't even talked about what we're looking for, but let's kind of inventory what we have here. With load number 1, I can say that I've got the arc cosine of 0.75, gives me an angle of 41.4 degrees. So now I have a triangle that looks like this. It's lagging, so I know that it's going to be positive like this. 41.4. And it's 1.5 megavolt amps. So when we read that, we should think immediately what? Which part of the triangle is that? That's the hypotenuse, isn't it? 1.5 megavolt amps. Okay. So we could break that up if we wanted to. Basic right triangle trig, pretty easy to do there. 1.5 meg times the cosine of 41.4 and the sine of 41.4. So we use the sine here, which will give you 0.992 megavars. Use the cosine over here, which is going to give you 1.125 watts. So if we wanted to, we could talk about S. S for load number 1 for the total would be what? 1.125 plus J 0.992 mega volt amps. Okay. So let's look at load number 2. So load number 2. Do the inverse cosine, the arc cosine of what was our power factor? 0.8. So that's 36.9 degrees. We've got then a triangle. It's a lagging power factor. So again, our triangle is upright. And when they said megawatts, we should think what? Yeah, that's the real portion down here on the horizontal. 2 megawatts. Okay. So we could say this. This is the calculation we did in the last problem here. Q is equal to 2 meg times the tangent of 36.9, which nets us 1.5 mega vars. Double check that. Yeah. So if I wanted to talk about then the complex power S for 2, we could say that that's 2 plus J 1.5 mega volt amps. Okay. So let's say that someone was asking about the voltage out here. What voltage do we have to have before the drop in the line? Okay. So that might be a good question. Maybe this would be page 4. Let's take what we've learned here. And put this together. I could really say that if I looked at the S total, what would that be? S1 plus S2, which is going to be, when you add those together, you should get 3.125 plus J 2.49. Megavolt amps. So if we ask that for the total per phase, what would that be equal to? S total divided by 3. So that turns out to be 1.042 plus J 0.831 megavolt amps. Okay. Well, let me try and do something with that. So I could combine those and I could just say, well, we've got a single phase equivalent system that looks like this. I've got a resistor here. I've got an inductor here. That's 0.4 and J 0.8. And then I've got this load, according to this over here. And this, if this is A, this would be the neutral. You okay with that? Okay, I should probably keep mega volt amps there, not lose the mega. So could I talk about this current here? I should be able to, shouldn't I? One thing that I may need is I may need to get this voltage here. What voltage is that? We said back on the original picture that from line to line the magnitude was 4.16 kilovolts. So this isn't line to line, but rather line to neutral, isn't it? So what's that going to be? 4.16 k volts divided by the square root of 3. Good? Okay. So didn't we have an equation where we said that S was equal to V RMS times I RMS conjugate? Okay. So I could say then that I RMS should be equal to V RMS divided by, whoops, not VRMS, should be just equal to S divided by VRMS, and I'll probably have to put the conjugate over there. Is that okay?
Would you take the conjugate of just S or the conjugate of the whole thing?
Or the denominator. You could do either one. I wouldn't do all of them at once. Well, actually, if you did all three, you'd still be okay, because it's an odd number. But don't do two. We okay?
Yeah, I mean, I was thinking if you divided the V on S over, then figure out that current and then conjugate is that.
Yeah, I mean, you could leave the conjugate off there, and then you'd be solving for the conjugate, and take the inverse conjugate, which would be the conjugate. Okay. So. Okay, so what's S on this thing? 1.042, and then because I'm going to do the conjugate, I've got minus J 0.831. That's from the conjugate there. And then I'm dividing by the voltage, which we said was what? 4.16 K divided by the square root of 3. And I'm just going to take that as a reference at 0. So when I get done with that, I have 554.7 at minus 38.6 amps RMS, which that's a big current. I mean, we talk about transferring power at 4,160. Yeah, 4,160 volts, and you got 554 amps. That's a lot of power there. So this would be for the folks that work with substations and things like that. So that's the current that's going through that. So I can, with that, I could figure out the voltage drop across there, couldn't I? Wouldn't that just be equal to that current I times the impedance that I have there? So I could talk about my V supply. That would be equal to the this voltage here that I need, 4.16 K over the square root of 3, plus then that, so 554.7 at an angle of minus 38.6. And I got to multiply that by the impedance, which is what? 0.4 plus J 0.8. Okay. This whole thing turns out to be 2,859.6 at 4.2 VRMS. Now that voltage is what? That's voltage, the phase voltage, which is line to neutral, right? Okay. So if I want to find the magnitude of the line voltage at the source, what would that be? 2859.6, and then what do I have to do to that? Multiply it by the square root of 3. Okay, so it turns out to be 4,953 volts, which we could put, I guess, in a context that we might recognize from the beginning, 4.95 k volts RMS. Okay, so that'd be the magnitude of the voltage out here, the line-to-line voltage. So you could afford that drop. Questions with that?
We were given the union delta and then y. It didn't even matter.
Yeah, we got the same power factor, or we got the same power calculation whether we were using a delta or y. So I was able to combine them into one without even worrying about that. Other questions?
So your supply voltage is the voltage across the inductor.
The supply voltage would be this voltage out here. And when I initially calculated it, so this is V supply right there. So that would be this one. And then when I convert it to line, I get the voltage that's out here. Other questions? So hopefully a fairly simple problem gets us to going back and looking at three-phase. I think the biggest thing about three-phase was dealing with all the nomenclature and things like that. When we get together next time, we'll continue reviewing and we'll talk about mutual inductance. That's probably a little more recent. We'll go through some problems there, and that'll get us pretty well done with that. So take care till then.